All right, folks, we're going to move into our next section here. Section number 3, we're going to talk about designing intermediate system to intermediate system routing. Not a topic that we talk about too often in a Cisco class. ISIS is a link state routing protocol. It's been around for quite some time, but it's typically a protocol that you're going to see running in a service provider environment. Nonetheless, we're going to spend some time talking about it. There are a lot of similarities to Ospf, being that it is a link state routing protocol, but there are also a lot of differences between ISIS and Ospf, and certainly EIGRP. One of the primary differences that we don't even really mention that much is the fact that ISIS is actually a layer 2 protocol. It's not even considered to be a network layer protocol, but it is a data link layer protocol that provides us the ability to share network layer reachability information and routing information. So we're going to do a quick section here about ISIS and talk about the benefit of the protocol itself and how it kind of sits in our environment, and then we'll see what the protocol is kind of all about. So we're going to start with a brief introduction. We're going to talk about the ISIS routing protocol. We're going to take a look at ISIS adjacencies and authentication, describe ISIS and Ospf similarities, being that they are both link state routing protocols. We're going to explore ISIS routing logic. What is an L1 router? What is an L2 router? How do we create the virtual backbone? What is an L1/L2 router? What are ISIS operations? And then we'll take a look at, in the final section or final topic of this section, examining the integration of ISIS for IPv6. So basically in this section, we're going to spend our time talking about really the design and the operation of ISIS. It is an OSI, or Open Systems Interconnect Dynamic Routing Protocol. ISIS, being that it is a data link layer protocol, has the ability to carry not only IP information, but CLNP routing information as well. We don't really see that too much these days. And ISIS, from a Cisco perspective, implements the ISIS using 3 fields in the NSAP address. We'll talk about that as well. It's called the area address, the system ID, and the NSEL, or NSEL. We'll dive into that in more detail in this section as well. We also have multi-topology support. That's nothing really new. EIGRP supports multiple physical and logical topologies. ISIS, of course, is going to do that, being that it is a link state routing protocol. It actually, in this particular case, only supports 2 topologies. We'll talk about what those topologies are a little bit later on, whereas Ospf supports technically 5 network types, 6 if you count loopback. And we'll see that ISIS supports both the standard IPv4 deployment options as well as IPv6 deployment options. All right, so let's go ahead and get started by talking about the routing protocol as a protocol itself. ISIS is an IGP routing protocol, meaning that it is something that we run inside of our enterprise. It is a link state routing protocol, so it does have a lot of similarities to Ospf. We do form adjacencies as an ISIS router. There is an adjacency process very similar to Ospf, and we use areas, although the area design in Ospf is a little bit more structured than it is in ISIS. The backbone, area 0 in ISIS, is virtual as opposed to a physical backbone where we actually have routers that have interfaces participating in a backbone. We use an overlay backbone in ISIS, and we create that backbone virtually by deploying L2 routers. We'll talk about that a little bit later on. It does form neighbor adjacencies. Like I said, we have areas, we exchange link state packets, we build a link state database. We also run Dijkstra's algorithm, or the SPF algorithm, to find the best path to each destination, and that ends up getting installed in the routing table. So it is a link state routing protocol. We use CLNS. I'll talk a little bit about CLNS a little bit later on. That's the connectionless mode network protocol. We also actually use something called CLNS, CLNP, excuse me, and CLNS, which is the connectionless mode network service. And we'll talk more about that as well. Back when Ospf and ISIS were developed, IP wasn't really the dominant protocol that it is today. So when we think of OSI, we think of the OSI model. But back then, ISO, the International Standards or International Organization of Standardization, created something similar to IP and UDP, and that's where CLNP and CLNS come into play. CLNP, the connectionless mode network protocol, was similar to IP in regard to its function at layer 3, and CLNS, the connectionless mode network service, was similar to UDP and its function at the transport layer. So that is certainly something different with ISIS in this particular case. We have some different terminology that we use as well. IS actually stands for intermediate system, and the idea is that a router is the intermediate system. And then we have an ES, which is an end system, and that would have ended up being our hosts in the enterprise. OSPF was developed originally by the IETF, the Internet Engineering Task Force. ISIS was originally developed by DEC, the Digital Electronic Corporation, for CLNS, not IP, and that's why it's called intermediate system to intermediate system. ISIS was actually adopted later on, or adapted, I should say, so it could also route IP, and that's where we get the term integrated ISIS. Integrated ISIS means that we were able to run ISIS using an IP environment. All right. So if we look at the diagram here, we can see that it is a link state routing protocol. So it's going to have a lot of the same characteristics as OSPF in the data structures that it has, as well as the different message types that we use to support ISIS routing. It does use CLNS to build the link state database. So again, that's very similar to IP/UDP in a sense. It is stable. It's very scalable, very fast to converge. So it is a very kind of modern type of routing protocol, even though it's been around for quite some time. And because we have the integrated version of ISIS now, it's easily extendable with new features, especially when we integrate those type, length, and value fields. It runs directly on OSI layer 2, which is the data link layer, which is an interesting concept because we're actually trying to do routing with it, right? And routing is something that we've always kind of considered to be a layer 3 concept, obviously, but actually OSPF and EIGRP are actually the only two routing protocols out of the 5 major routing protocols that we typically talk about that actually operate at layer 3. EIGRP is protocol 88, OSPF is protocol 89, but RIP operates as an application over UDP, and BGP operates as an application over TCP, and ISIS operates at the data link layer level. So in reality, we only actually have 2 routing protocols that function directly as a layer 3, traditional kind of layer 3 protocol. All right. So we have end systems, which are our ES components. Those are the ones that are not routing. And we have our intermediate systems, which are our routers. So ISIS is an OSI link state routing protocol, very stable, very scalable, very fast to converge. Again, designed as an IGP for CLNS, which is part of the overall OSI protocol suite. The OSI protocol suite layer 3 protocol, like I said, is CLNP. That's kind of equivalent to IP in this particular case. And we use CLNS addresses to identify routers and build the link state database. So there's some kind of correlation, at least to endpoint addressing with CLNS, even though we kind of equate that to the transport layer function. It's not directly relatable to the transport layer function. We certainly don't have any addressing components in UDP, but that is the purpose of it. We'll get it into more detail about CLNS a little bit later on as well. All right. Now, one of the things that I briefly mentioned is the extensibility of the protocol itself. ISIS it encodes data in what we call a type length value format. And this is not unique to ISIS. Ospf uses TLVs and EIGRP uses TLVs, but these type length value fields are, I often describe them as kind of generic Tupperware containers. Just a clear plastic container that can be used for all kinds of things. And the type, it would be equivalent to, if I extend the analogy, would be equivalent to putting a temporary label on that container that says, this is the type of container that I'm creating. And that type of container could be a certain size, it could be a certain shape, it could have certain features, whatever, but it's still just kind of a generic container. The length of the container would be how much information it can actually store. Basically, the size of the container itself, and then the value of that container would be what's inside of the container itself. All right, does that make sense? So think of these type length value fields as just kind of generic fields that can store lots and lots of information. And in turn, that makes ISIS very extensible, meaning that it can really kind of be customized to support all kinds of different features. It is a very flexible protocol, very easy to tune, very easy to incorporate into different types of technologies like MPLS, traffic engineering, and so on. As I mentioned, there are two types of systems. There are non-routing nodes in the ISIS environment. Those are my host nodes. And then the ones that actually do the heavy lifting, the intermediate systems, which are my routers in the system itself. All right, so in the ISO concepts, we refer to routers as intermediate systems. So ISIS is really a protocol that allows routers to exchange information with each other. And that's really generally the purpose of any dynamic routing protocol, is to provide a mechanism for those routing protocols to exchange information with each other. We use CLNS to provide that connectionless delivery of data. Connectionless meaning that there's no guaranteed delivery. The packets are not sequenced, they're not acknowledged. But that's pretty typical for a layer 3 protocol, which is what CLNP is. It's the connectionless layer 3 protocol that allows that delivery. We use CLNS addresses to identify the routers. We build our link state database. Those CLNS addresses are called NSAPs, or what we refer to as Network Service Access Points. And like I mentioned previously, they have three major components. We have the area identifier, which is the prefix, followed by a system identifier, and then an end selector. And the end selector refers to the network service user, like the transport protocol or the routing layer. So think of an end selector field almost equivalent to say like a protocol field in the IP header, or even a type field in a layer 2 Ethernet 2 header. It allows us to identify what's being transported and so on. All right, we'll talk about the addressing scheme a little bit later on when we get into the routing logic and how adjacencies are formed and so on. All right. Like I said, the protocol is very extensible through the use of type length value fields. These are called tuples because they actually have 3 components: type, length, and value. That's what a tuple represents. And so we can really kind of extend ISIS to really kind of any type of application, including things like IPv6, because we just simply create these new Tupperware containers, if you will, these tuple containers, so that we can add the new features to the protocol itself. The intermediate system communication is provided by using layer 2 of the OSI model, so there's really no need to have any IP connectivity or to run upper layer protocols. We simply use layer 2 for the transport of the information. All right, so let's take a look at some of the other characteristics of the protocol itself. It does support VLSM, so it is what we refer to as a classless routing protocol, but Ospf also by default was a classless routing protocol. We do use Dijkstra's algorithm, Dijkstras. That's Edsger Dijkstra, the gentleman that came up with the shortest path first concept. Not specific to routing, but it was adapted to routing. We do use hellos. We use link state packets to exchange information. We don't get into the specific message types too much in this class, but in some of the other advanced routing classes, we do tend to get into a little bit more detail about the overall concept of message types, and there are multiple message types that are available. This is an interesting concept right here. We do have cost as our metric, much like Ospf uses cost as a metric in its operation. But the cost in Ospf is calculated based on an inverse proportion of the bandwidth of the interface. 10 to the power of 8 divided by the link bandwidth in bits per second. And we round that down to a whole number. We don't use any floating point math in those calculations. Only the egress interfaces matter in that particular case, and that becomes the actual cost of those individual interfaces. In the concept of ISIS, we can modify the cost value of the specific interfaces, but the reality is that the interfaces have all the same cost. Doesn't matter if it's gigabit, doesn't matter if it's fast Ethernet, doesn't matter if it's terabit. We're going to default the cost to 10. That is something that we will spend some time talking about a little bit later on with regard to how we actually differentiate between those different speed links. But it is an interesting concept to ISIS. ISIS as a link state routing protocol does operate very efficiently. It doesn't require a whole lot of bandwidth to function, a lot of memory, a lot of CPU processing to carry information. It is a data link layer protocol, so it's a little bit more lightweight than maybe your traditional routing protocols or even your application layer routing protocols like BGP or RIP. And it does use a wide metric. So it uses a 24-bit link metric and a 32-bit path metric. But the link costs default to 10, which means that ISIS by default, unless you modify the behavior, actually operates on almost like a RIP routing protocol on a hop by hop basis. All right. I don't know why that guy showed up there, but let's move that back over here. All right. So because every link ends up having the same cost, it's almost like we're doing hop by hop routing as opposed to doing some sort of kind of bandwidth based routing in like we would with OSPF, where we have actual link costs and the cumulative cost of the path ends up determining what the best path is. We'll probably get into that later on when we talk about the routing logic with ISIS, about how we would manage that. ISIS as a link state routing protocol, of course, is very similar to OSPF, and it does provide for the ability to divide the routing domain up into multiple areas. So let's talk about that a little bit. All right. Again, like I said, ISIS rides directly on top of an Ethernet header. It uses its own header format. It's not actually encapsulated inside of an IP packet like EIGRP and OSPF are. So we'll have our Ethernet header, we'll have our ISIS header, we'll have our ISIS data, and then we'll have our frame check sequence after that. It is a very scalable routing protocol, which is why it's actually used for large service provider network backbones. And so let's talk about some of the functions of the two routing levels and get into that detail. ISIS uses different areas where the entire router sits in an area. So that's different than OSPF already, right? In OSPF, each individual interface sits in an area. And in fact, you could have multiple interfaces that are participating in different areas. There is no backbone area per se. The backbone is actually formed by a string of routers that we configure. There are three types of routers that exist in an ISIS environment. There's a level 1 system router. This is what we would refer to as an intra-area router. It only knows what the local area looks like, and it only learns prefixes from its own area. It creates what we call a level 1 link state database and the shortest path tree for that particular area. The next type of router that we have is a level 2 system router. This is what we refer to as a backbone router. It knows all of the intra-area and inter-area routes. It creates this level 2 link state database, and it runs the shortest path first tree for the backbone. And then we have our final one, which is called a level 1-2 system router. This is a router that basically does both roles. It creates a separate link state database for level 1 and level 2. It runs 2 SPF trees, one for each of those databases. For Cisco devices, they're going to default to level 1-2 in Cisco iOS. All right. Now, similar to other routing protocols like OSPF and EIGRP, ISIS routers will send hello packets to form adjacencies. When you send and receive those hello packets, you're going to end up forming that neighbor adjacency, but routers will only form a neighbor adjacencies with other routers that operate at the same level. So an L1 to L1 router, for example, would create a single area, maybe area 1, and those L1 to L1 routers would become adjacent. In that particular case, you would only have a single area, so those two routers are configured as L1 routers. It would look something like this. So I would have a router here, I would have a router here. Both of these are defined as L1 routers. They would form their adjacency, and this would become, say, area 1. All right. Now, and by the way, those level 1 routers only know really what exists in that area. If a level 1 router wants to reach something outside of its area, it has to use a level 2 router. So in each area, we would configure one router as a level 1-2 router. That would look something similar to this. So I'd have, oops, that's not going to work. Let's see. I don't know why that changed. In fact, let me go to a really small pen here because I'm going to run out of space. So let's say we have our level 1 router here, level 1 router here. These guys are L1 adjacent, and this forms an area. And then maybe I have another set of L1 routers over here. Well, then L1 adjacency. And that might form, say, area number 2, and we'll just call this area number 1. In order for these two routers here to form an adjacency, they're going to have to establish a level 2 adjacency because they have essentially separate link state databases. So these routers on the edge would end up having to be L1/L2 routers to be able to form that adjacency. All right. What we refer to basically as a level 2 router. All right. Now the level 1/2 routers will establish two different adjacencies. They'll form an L1 adjacency with the other router that's in the same area, which is the router on the right and the left respectively, and then they'll form a level 2 adjacency with the routers in the other areas. And that essentially would create my backbone in this particular case. All right. Now it can get a little bit more complicated than that, especially if you have multiple areas. Let me, in fact, draw kind of a bigger diagram here. I don't want to draw too many routers, but let's take a look at a scenario that we have where we have more routers in the topology. So let's say, as an example here, we have area 3. So we'll just call this area 3. And we have a router here, we have a router here, we have a router here, and let's create another area over here. We'll call this area 4. We have a router here, and down here we'll have area number 1, and let's say we have a couple of routers in that area, and then over here we might have area number 2, and we have a router in area number 2. Actually, a couple of routers in area number 2. So in this particular scenario, not only do we have to form the L1 adjacencies, but we also have to establish a backbone. You know, there has to be some congruency, there has to be some connectivity between all of the areas at level 2 to create that overlay backbone or that virtual backbone that we create in ISIS. So our level 1 adjacencies would look something like this. We would have an L1 adjacency here. We'll just put L1 for the color. We might have an L1 adjacency here. We might have a L1 adjacency here, L1 adjacency here, possibly even an L1 adjacency there, depending on whether or not those routers share a common subnet on that particular interface. But those would be my L1 routers, and this guy would still be an L1 router in its own area, even though it doesn't necessarily have any adjacencies. It would still have to be functioning as an L1 router to be able to build that link state database for area number 4. All right, and to create this virtual backbone, I might have my L2 connections. So we would have an L2 adjacency between those two routers. And in this particular case, we wouldn't necessarily have to have an L2 relationship between all of the routers in this topology, but we would have to extend that L2 relationship through that area so that we can then establish the L2 relationship between area 3 and area 1. We would have to continue that L2 relationship here and then eventually extend that L2 relationship over to area 2. So in this sense, we're not creating a separate physical backbone. We're creating this logical backbone that goes through all of the different areas and ties or links all of those different areas together. So it is a significant difference than what we would see with like a traditional OSPF hierarchy. Make sense? All right. So that's certainly different in this sense when we talk about kind of joining the domain together. We have both essentially the areas that we're creating. Here are some of the terms that I've kind of referenced throughout this discussion. An area is a group of contiguous networks and attached hosts that are specific to be in an area by a that are specified, to be in an area by you, the administrator. The domain is a collection of connected areas, what I was basically just drawing there a second ago. Routing domains provide full connectivity to all end systems within them. Think of a routing domain as kind of like an autonomous system, right? It's a very similar concept. OSPF, the autonomous system, is the entire architecture, including the backbone and the non-backbone areas. The ISIS routing domain is the network where all the routers are running integrated ISIS to be able to facilitate the exchange of that routing information and that reachability information within the domain. So ISIS actually exchanges routing information using link state packets, very similar to link state advertisements in OSPF. Inside of a link state packet, you would have prefixes, one or more prefixes that are included. You would have adjacency information. You would have metric information. But don't confuse the acronym LSP for label switched path in MPLS. It's the same acronym, but it's not the same concept, obviously. A lot of people will see LSPs and they have some experience utilizing MPLS and they kind of get confused. All right. Each router is going to create a link state packet. In that link state packet, we will find our directly connected networks that are used to advertise ISIS reachability information. And then those routes, we form adjacencies and we share that information. If we have two routers that are in the same area, they're going to establish that level 1 neighbor adjacency. And we can see here by the definition, level 1 routing is routing within the area. All level 1 routers know only the topology of their own area. They can have a level 1 or have level 1 to level 1 and level 2 neighbors. The wording there is a little bit strange, but they can have level 1 to level 1 relationships, or they can have level 1 and level 2 neighbors, as long as the neighbor's running some sort of level 1 routing, right? It doesn't mean that we cannot form an adjacency with an L1/L2 router, and that's basically what they're saying in this case. We have our level 1 link state database, and that's all of our intra-area routing information. We use the closest level 1 or level 2 routers in our own area to send packets out of the area. Would have to actually be an L1/L2 router because the router would still have to be participating in the area. All right. These routers would end up flooding their link state packets with within the area, so everybody knows about all of the link state packets in that area. The routers will add each other's link state packets to their database, and then we can run our shortest path first algorithm on our level 1 database to figure out what the shortest path first is to each destination. All right. ISIS also uses something called the DIS pseudo node. It is similar to the concept of the DR-BDR election process that we talked about briefly in OSPF to reduce unneeded flooding within the domain. We'll talk maybe a little bit more about the DIS or distribution node or pseudo node a little bit later on. Now, if we do want to connect area X, whatever area it might be, to another area, we're going to need that level 2 routing. So we would actually convert a router at the perimeter of the area into a level 1-2 router. And at that moment, we will start it'll reset adjacencies if we convert that router and try to reestablish adjacencies, and then we will be able to establish not only level 1 adjacencies, but also level 2 adjacencies. Once we do that, we create that second database. It's a level 2 database on that particular router. So we have our original level 1 database and our level 1 link state packets, but we now also have a level 2 database, and we're going to be generating level 2 link state packets and prefixes for the interfaces that are directly connected and advertised in ISIS. So each ISIS router only creates a single link state packet for each level, and those link state packets, almost like a link state update in Ospf, is going to carry multiple prefixes for that destination. All right. So again, once I've converted one of the routers in the topology to a level 1, level 2 router, we're going to reform a level 1 neighbor adjacency with the router that was previously running level 1. We're going to exchange our level 1 link state packets, and then the router that is a level 1, level 2 router will get those level 1 link state packets from the other router. It's going to then copy that prefix information from its level 1 database into the LSPs that are going to be generated for the level 2 database. All right. At that point now, we can create additional areas, and we would create those other areas in the same manner. We don't really have any connectivity between those areas because we haven't formed adjacencies, but we could continue down the path and create that configuration. So I think you guys have a pretty good idea of how we establish those adjacencies. All right. The ISIS backbone, like I said, is a contiguous chain of level 2 capable routers. We have a diagram here that kind of describes that. So in the case here, we see that we have area ID number 2, which we have our 2 level 1 routers in that area that are going to exchange. Ooh, that's not nice. There we go. That are going to exchange that routing information in that area, right? That's our level 1 adjacency. But this router here at the perimeter is going to be running L1/L2, which then in turn would extend the backbone. And if I was to actually go through, let me go ahead and change my pen color here because we got a bunch of different interface red lines here. We can actually see that our backbone extends from here to here, from here to here, there, as a level 2 router. Looks like we also have kind of those connections running as L2, 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 and L2. So that's the virtual backbone that we've created for the connectivity between these different areas. All right. That backbone, as long as it's contiguous, will allow the exchange of level 1 reachability information, but not with L1 link state packets, as we're going to use our L2 link state packets. So the backbone cannot be interrupted. We can have redundant links, and in this case we do kind of in area 1, which is basically an L2 only area. And we have, every single link in that area is L2, so that's going to provide some redundancy. If one of those routers were to fail, well, it's interesting. They do have the redundancy all the way, within area 1. They don't really have any redundancy getting to the other areas, but that's not really the point of this particular diagram. The point here is just to demonstrate that we have to have a contiguous L2 backbone. All right. So area ID 1 has level 2 routers only in the core. Area ID 2 through all of the rest of the areas have level 1 and level 2 routers that are connecting areas to the backbone. All of those level 2 capable routers make up that backbone for the network, and inter-area traffic has to cross the backbone. All of our L2 adjacencies are shown as red connections here, and the L1 adjacencies are shown as blue connections here. Is there a downside to running an only L2 area? Not really. I mean, the link state packets are formatted the same way. It's just a matter of whether or not it contains intra-area information or inter-area and intra-area information. So the level 2 connections are going to exchange more information because they're exchanging both intra and inter-area information. All right, so the traffic between area 3 and area 4 would have to go through that backbone. All right, now traditionally in OSPF, that would mean that we would have to go through an area border router, a router that's attached directly to the backbone, and we would not really have direct communication from one area to the other. But in this particular case, we have an L2 link between the areas, so that means that we can facilitate that communication through that L2 link. If for some reason that link were to fail, then we can use an alternate path. We can use actually various alternate paths to get to from one area to the next in this particular case. You could certainly have more than one router acting as a L2 link between other areas as well, but it's not depicted in this particular topology here. All right. Here's a diagram that basically describes, again, the same general concept. This level 1 routers can establish their level 1 adjacencies. So you can see between the router on the left in area 490002 and the router on the right, kind of on the bottom right there, we have both L1 and L2 adjacencies as well. And then we have our backbone that kind of extends through the network. All right. The bottom left router has only a level 1 adjacency. So the backbone only has to interconnect the areas. It does not have to interconnect every single router. That's a really important concept as well. As long as all of the areas are interconnected, which allows for that inter-area link state packet exchange of information, that's what really matters. All right. And the bottom left router would only have intra-area routing information available to it, which would then be exchanged by the router on the top right in that particular area. Okay. A level 1 router knows the topology only for its area. It has a level 1 or level 1 and level 2 adjacency in that area. It has a level 1 link state database with all of the information for the intra-area routing for that particular area, whatever area it might belong to. We use our closest level 1/level 2 router or level 2 router to send data out of the area. And we can see that that's done in this particular case. Level 1 or level 2 routers can have neighbors in any area. So because we are running as level 2, we have the ability for inter-area packet exchange, but it will maintain 2 separate link state databases. A level 1 link state database for all of the intra-area routing information, and a level 2 link state database for all of the inter-area routing information. We also run 2 different shortest path first processes, and that means that, of course, those routers are going to have more processing requirements, more memory requirements, and so on. All right. All right. So let's take a look at, well, here we're kind of seeing the same concept, right? Level 1 link is only for level 1 adjacencies within the same area. Level 2 link is for level 2 adjacencies, but those can be used within the area or they can be used between areas to route between different areas. Level 1 and level 2 links are used for level 1 and level 2 adjacencies. We see that on the two routers in the top domain there. Okay? So in our next section here, we're going to talk about the adjacency process. We're going to talk about authentication as well. The sub-network dependent functions of routing that are provided by ISIS are used for the exchange of routing information, right? We need to establish essentially the adjacencies. We need to maintain those adjacencies. We need to be able to exchange routing information or network layer reachability information. And it's no different than what we would see with any type of routing protocol, right? That's the whole purpose of the routing protocols. And in fact, we talked about this briefly in one of our previous sections. 3 things that every single routing protocol has. Message types that allow us to exchange routing information or establish adjacencies or maintain adjacencies or establish the change of information. And those are the different message types that are necessary to facilitate that. We have our data structures, like a neighbor table, a topology table, and a routing table, and we have our algorithm. ISIS is no different. Just because it operates at layer 2 of the OSI model doesn't mean that it functions differently here. All right. So what you're seeing in this particular diagram is really an extension of what we were talking about previously, different roles that the routers play to form ISIS adjacencies between them. And the differences that we see are based on the topology, and that's going to influence how we form those adjacencies. 2 different routers will become neighbors if they have parameters that they agree on. All right, so if we have a common network segment and we're in the same area, we're going to form a level 1 adjacency. If we have we're in a common network segment, but we're in different areas, we would have to form a level 2 adjacency. Now, ISIS is a link state routing protocol, and as I mentioned before, it's highly scalable, probably more scalable than OSPF, very, very fast to converge, and so on. All right. And we mentioned this before as well. The book kind of talks about it again. The OSI protocol suite layer 3 protocol that's used in this case is CLNP, and we use our CLNS addresses to identify routers and build that link state database. All right. There's nothing wrong with forming both level 1 and level 2 adjacencies as long as the routers can support that functionality, right? In other words, they have enough processing power, enough memory to be able to facilitate that communication. We use CLNS, the Connectionless Network Service, to form adjacencies between the routers. In the diagram here, we can see router A on the left is identified. We'll talk about the addressing component there, the 49.1234.1111.1111.1111.000 or .00. That is that tuple field that we use to identify the node. We talked a little bit about that briefly in the beginning. We'll get into that in a little bit more detail as we kind of go through the rest of these sections here. So we form that adjacency. So in this particular case, router A and router B have both types of adjacencies. It's not really depicted here, but we could have both of those level 1 and level 2 adjacencies. The neighbor authentication, just like we have authentication available within OSPF and authentication available within EIGRP, allows us to identify a authentication and integrity mechanism that we can use to establish those adjacencies. And you can see that the adjacencies are going to be established based on the router type, level 1 or level 2, and the area address. All right. Now, unlike OSPF that has 5/6 different network types, point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, broadcast, NBMA, and loopback. In ISIS, we only have two network types, point-to-point and broadcast. ISIS doesn't have things like NBMA or point-to-multipoint or point-to-multipoint non-broadcast, but we do generate different types of hello packets, IIH packets, as you can see there, to exchange that adjacency. All right. Point-to-point topologies would include things like a point-to-point serial link. These are going to be common for level 1 and level 2 adjacencies. But within that hello packet, the level 1, level 2, or level 1 and level 2 information gets announced. So we're actually kind of separating the information that's going to be advertised. Level 1 routers obviously are going to be within the same area. They're going to exchange those hellos to specify the level 1 adjacency information. Level 2 routers are going to be in different areas, and they're going to have different types of PDUs to establish their adjacencies. All right. Now, as an L1/L2 router, I don't generate a third type of hello. I simply use the IIH PDU for level 1 and the IIH PDU for level 2 to establish those adjacencies there. All right. If I have two level 1 routers that are physically connected to each other, but they're not in the same area, they're not going to be able to establish an adjacency because the area ID doesn't match in the address. All right. If I do have authentication configured, we don't actually take a look at how that authentication is established in this case, but if I do have authentication configured, it makes sense to say that we would have to have similar authentication properties. All right, now in this particular case, you can see that all 4 of these routers are in the same area. The area ID is identified with the 49.1234 value. And they're going to have the same password that's going to allow them to establish an adjacency. They're going to form basically one area, and they're going to accept those level 1 IIH PDUs only from their own area to establish those level 1 adjacencies with their own era, with the other routers that are level 1 adjacent. All right. If we have routers from a second area, we'll accept the level 1 IIH PDUs, but only from that area as well. And we'll have to use the level 2 information to process level 2 hellos and level 2 hello IIH PDUs to establish those level 2 adjacencies. All right. Again, we'll get into the details of the addressing a little bit later on here. And talk about how the addressing is affected. How do we select those addresses? Is it arbitrary? Is it something that we need to, consider from a hierarchical standpoint, and so on? ISIS, integrated ISIS, as I mentioned before, is just really a different flavor of ISIS, where we've actually decided to carry IP information over ISIS. And the original RFC was RFC 1195. Integrated ISIS allows us to tag routing information. We'll see this in the routing logic section a little bit later on, to share information about network reachability. All right. It is an independent protocol from other protocols. So we do have the option of running IP only. That's what we would refer to as a pure IP domain. We route only IP traffic, but we support the forwarding and processing of the OSI packets, which are the CLNP and CLNS packets that are required to establish the ISIS domain. We also have a pure ISO domain, which carries only the ISO traffic in the network, including whatever would be necessary to establish the ISIS domain. And then finally, we have a dual domain. That's where we're routing both IP and OSI CLNP traffic simultaneously. Most likely what you're going to see in most environments today is a pure IP domain. That doesn't mean that you're not running CLNP or CLNS. That's always going to be required to establish the ISIS adjacencies and to maintain the ISIS domain. All right. But, you know, obviously IP is pretty much the standard protocol that we use today. Now there are, because ISIS is a link state routing protocol, obviously there are going to be a lot of similarities to what we see in OSPF and ISIS. Both of these protocols are what we would consider interior gateway protocols, meaning that these are protocols that we're going to run inside of our enterprise to allow us to exchange network layer reachability information within that enterprise. Both of them are link state, which means they both run the shortest path first algorithm, meaning Dijkstra's algorithm. They both use the concept of areas, although in OSPF, obviously the area concept is based on interface concepts as opposed to router concepts in ISIS. Obviously in ISIS, the router goes into an area, not the interface. Very fast to converge, highly scalable. I would say that OSPF is probably a better choice because of the way it handles metric information and routing information, basically the fact that it's a layer 3 protocol. But as long as you understand the concept of how ISIS deals with cost and you understand how to evaluate those paths and modify the ISIS configuration appropriately, it's just as scalable and just as flexible as OSPF. Very quick to converge, highly scalable protocols. They are hierarchical in nature, and they're both highly adaptable to large enterprise networks, service provider environments, and so on. ISIS is typically, like I said, going to be used in most large service provider environments, whereas OSPF is going to be more likely to be used as a protocol in, kind of an internal enterprise, if you will. All right. So let's take a look at the area design. What are some of the options for area design? And how do we compare this to OSPF? OSPF, as we've talked about many times, uses a contiguous centralized backbone, and all of the other non-backbone areas are going to attach to that backbone. We use our area border routers to establish those adjacencies and to establish that relationship between our non-backbone areas and our backbone areas. But in OSPF, we are constrained by the fact that the area 0 is a centralized contiguous area. And then all of the other areas have to be physically attached to area 0. The border between area 0 and the non-backbone areas is an ABR or multiple ABRs. We're not limited to just using one ABR. And then the interfaces themselves go into the area. So we would have at least one interface in area 0 and other interfaces that are not in area 0. All right. Now, in this case, we have to have a very consistent and planned out IP addressing structure to gain the benefit of the components that we talked about yesterday, namely summarization, so that we can summarize addresses into the backbone, reduce the size of our link state databases, and be able to route information more efficiently throughout the OSPF domain. All right. Now, if I were to look at this kind of similarly in comparison, ISIS, we've already mentioned this a couple of times, has a hierarchy of level 1 and level 2 routers, or level 1 - level 2 routers. And the area borders lie on the links themselves. Now, the routers become level 1 routers or level 2 routers or level 1, level 2 routers, but the backbone is extended by simply adding layer 2 links to establish that layer 2 adjacency. So I would say in this particular case that the idea of the backbone in ISIS is somewhat arbitrary. We obviously have to have a contiguous backbone that links all of the areas together, not all the routers together, but at least links all the areas together. But how you decide to do that is entirely up to you, because you can have multiple entry points into an area. Now, I will say this, any routers that share a physical link but are in different areas would have to have a level 2 database function on them. You would not be able to get away with not having a level 2 functionality on those routers, because one of the checks, if you will, in establishing an adjacency is either the areas have to match and we can form an L1 adjacency, or the areas, if the areas are different, again, the routers go into an area, we would have to form a level 2 adjacency. All right. So, but the ISIS backbone is essentially a contiguous link or chain of level 2 capable routers that span across all the areas and join those areas together. All right. OSPF does provide for the incorporation of link state advertisements, but these link state advertisements get sent out kind of individually as needed. So in the case of OSPF, you might see lots and lots of different LSAs that are being sent, whereas ISIS updates get grouped by the router and they're sent as one link state packet. I kind of mentioned that previously when we were going through the kind of the description of the protocol itself. As the network complexity goes up, the number of ISIS packets doesn't go up, because we're still just carrying that reachability information in the same packet itself. Each packet does have to be routed. Routing does take resources, so more packets do represent potentially a larger impact on the network, of course. ISIS does use a lot less resources. We can have up to 1,000 routers in a single area, meaning that ISIS is definitely a lot more scalable than, say, OSPF. OSPF also runs at the network layer, it runs over IP, whereas, again, ISIS runs through CLNS at layer 2. All right. We don't really have the concept of or the idea of an area border router in ISIS. We can see in this particular case, we have different LSA types. I briefly talked about those LSA types in one of our previous sections when we were talking about OSPF. Router LSAs, those are my type 1 LSAs. These are generated by everybody in OSPF, and they describe the links that essentially that router owns, basically. Network LSAs, these are my type 2 LSAs. These are generated by DRs and BDRs to describe the multi-access network that those routers are responsible for managing. Type 3 LSAs are going to be generated by ABRs. External LSAs are going to be generated by ASBRs, and so on. We talked about, the type 5s, the type 4s, the type 3s, type 7s, if it's an ASBR and a special area type, and so on. We don't really have that concept in ISIS. So in that sense, ISIS is a little bit more efficient than OSPF, making use of the CPU resources more efficiently when we're processing routing updates. So we have less or fewer link state packets to process, but that mechanism that ISIS uses to install and withdraw prefixes is also less processor intensive, less memory intensive, and so on. All right. And we use net addresses. I'm going to talk about the addressing component here in a minute, because that's certainly a major thing to understand about ISIS is how does the addressing piece work. All right. So let's talk a little bit about that and then we'll get into the domain establishment and whatnot. ISIS, as I mentioned before, is a link state interior gateway routing protocol. It does run Dijkstra's algorithm. It does run the shortest path first algorithm to create the database of the network's topology. And then from that database, we determine the shortest path to our destination. Again, Ospf was developed by IETF. ISIS is an ANSI ISO protocol that was developed by Digital Equipment Corporation, DECnet, which, by the way, I don't know if you guys know the history or not, but if you've been in IT as long as I've been in IT, you have probably heard of 3Com, right? 3Com is a manufacturer, a vendor that created Ethernet adapters and connectivity options for connecting to the network. But 3Com actually stands for 3 companies. That's what it was an abbreviation for 3 companies. And those 3 companies were Digital Electronic Corporation, Intel, and Xerox, what we called the DIX Consortium, DIX Consortium. And those were 3 companies that were kind of integral in establishing how modern networks work today. In fact, Ethernet 2, which is the same primary Ethernet mechanism that we use today, was actually developed by Xerox. And Xerox doesn't exist anymore specifically as a company, but they have left their mark anyway. All right. Now, ISIS does use a slightly different set of terminology than Ospf for naming the protocol packets themselves. The packet that ISIS routers send to each other describing the network topology are called link state protocol data units, or link state PDUs, or LSPs, and we mentioned that previously. So in addition to describing the network topology that the router knows about, whether it's the L1 topology within the area, the intra-area topology, or the L2 topology between areas, the inter-area topology, the link state PDUs include IP routes. There's a checksum component. There's other information that's included in that as well. Similar to Ospf, all ISIS routers place information in that received link state PDU into their link state database. And then all the routers have essentially the same view of the network topology, right? A complete picture of the network topology, which is, a common characteristic of any kind of link state routing protocol. And then ISIS runs the shortest path first algorithm on the information in that link state database to determine the shortest path to each destination on the network. And then we place things like the destination / next hop pairs that result from the SPF calculation into the ISIS routing database. However, unlike other IP routing protocols, which typically run on TCP in the case of BGP, or UDP in the case of RIP, or IP in the case of Ospf or EIGRP, these are all layer 4 or layer 3 protocols. As we mentioned previously, ISIS runs directly on the data link layer. So the addressing functionality, the way that we establish the ISIS domain, is going to be different because as a result, the interface that runs ISIS doesn't need IP addresses to actually exchange ISIS information. We don't need to actually configure an INET family on interfaces running ISIS. Instead, the routers need an IP address, which makes the routing configuration similar, but not necessarily better per se. All right. But because it was developed as part of the OSI network protocols and not part of TCP/IP, we don't use traditional IP addressing. ISIS addresses are called NETs, N-E-T-S, or network entity titles. That's what NET stands for, network entity titles. IP addresses are 32 bits long. They're normally written in dotted decimal format with quad notation, 10.10.10.10. Nets can actually be anywhere from 8 to 20 bytes long. Generally, they're about 10 bytes long, and they're written as an address that has basically 3 parts. We don't see it here, but I think we saw it previously. Let me just go back to where we were. We saw that. I think it was right here, right? So I'll leave that up while I'm kind of talking about this concept. 49.1234.2222.2222.2222.0.0 represents the address. So the first part of the address is called the area identifier. All right, that's the first 3 bytes, and that represents the area ID. The first byte in this particular example, 49, is what we call the AFI, the address family identifier, which is equivalent to the IP address space that's assigned to the whole autonomous system. So everybody within the ISIS domain would have a similar number in this particular case. The AFI value 49 is actually used for private addressing. We'll see a breakdown of this a little bit later on, but that's equivalent to, say, like the RFC 19 address, RFC 1918 address space. The second number, the second 2 bytes of are the area ID. So 1, 2, 3, 4 represents the area number in this particular case. So we can see that router B, router C, router D, router A are all in a common area. The next part of the address, which is the next 6 bytes, identify the node that is this router in that network. Okay, so the system identifier, which is the 2222.2222.2222.0.0, is equivalent to the host or address portion of an IP address. We can choose any value for the system identifier, but a commonly used method is to use what we call BCD, which is binary coded decimal, which takes the router's IP address, maybe an address that you might have assigned to, say, a loopback interface, filling in all leading zeros, and then repositioning the decimal points to form the 3 2-byte numbers. So if I had an IP address, for example, of 192.168.1.2, I would maybe pad those numbers, and the result would be 192.168.001.002. Rearranging the decimal points then would give me the system identifier of 1921.6800.1002. Another common way would be to assign the system identifier to start with the router's MAC address, which happens to be 6 bytes, and then we just simply rearrange the decimal points to create the 3 2-byte numbers. So if the MAC address is 001B 633186BE, the system identifier would end up being 001B 633186BE, grouped into those blocks. The last 2 digits, so the 2222222222 is what we would refer to as the system identifier. And then the last 2 digits represent the net selector. Those are the final 2 bytes. This is called the ENSLD. In the case of ISIS or integrated ISIS, they always have to be a 00, which indicates this particular system. All right. So that's kind of how the address breaks down. Let me get back to where we were. And we will continue on with our discussion. I think this is where we were. All right. So it's not overly complex, right? It is, the address, like I said, is kind of broken up really into two parts, being that the end cell is always going to be a 0, 0. Now, as far as the protocol itself, obviously the area borders on the links. Each router is only in one area, not the interfaces like Ospf. And then we simply extend the backbone by having those L2 adjacencies. Fewer link state packets, like I said. It runs on top of the data link layer. I kind of summarized all this already. Both Ospf and ISIS are link state protocols. They're both very fast to converge. In Ospf, customization and adding different features to Ospf is a little bit more difficult than ISIS. We have to create new link state advertisements to be able to do that. But because we use those TLV strings and tuples in ISIS, it makes it very simple to extend functionality to ISIS. You could choose to run Ospf over ISIS. Ospf is obviously probably a little bit more optimized. It was designed based on IP, and most enterprise networks are going to run IP. And we do have other functionality within Ospf that can be useful. The ability to be able to run things like special area types, stub areas, totally stubby areas, not so stubby areas, and so on. And how Ospf handles metric calculations a little bit better than ISIS, where we have a default metric of 10 on every interface. But there are pluses and minuses to both protocols. By the way, we're not stuck with that metric of 10. We can actually change that behavior on a per link basis or on a global ISIS routing basis. So I mentioned already kind of how the address is broken up. All right. We use the NSAP address to identify the router in the topology. So ISIS requires that NSAP address to function. The AFI is the first part of the address, which I had indicated. And you can see here kind of a breakdown of the different AFIs that are available. 39, the ISO data country code. 45 is E.164. 47 is ISO code designator, ICD, and 49 is locally administered or private. I don't know that it's necessary that you guys remember this for the exam. I don't think they're going to be asking you about this on the exam, but we kind of already broke down what the address, how the address is represented. But the address itself is supposed to represent the entire node, not an interface. So that's an interesting concept as well. And I would say it's kind of similar to the idea of a router ID, right? In Ospf, the router ID allows us to identify the node, and it's unique to that particular node throughout the entire autonomous system. Although router IDs don't have the same structure, the same kind of defined structure that an NSAP address has, it's kind of a similar concept that allows us to identify the node itself. All right. So the NSAP address, I already kind of broke this down, but it is a maximum of 20 bytes. The higher order bits identify the inter-area structure, and the lower order bits identify the system within the area. So we have the ability to identify the AFI, the IDI. I kind of broke this down previously when we were talking about how the address breaks down a little bit earlier, right? But it's basically kind of a combination of the IP address and the upper layer protocols in an IP header. We have a maximum size of 20 bytes. The high order bits identify the inter-area structure. The low order bits identify the unique systems within the area. And there are different address formats. I kind of broke down one of the common address formats, but there are different formats. So let's kind of break this down again. Cisco implementation of ISIS distinguishes three fields in the NSAP address. Those three fields I already broke down: the area address, the system ID, and the ENSL. The area address is a variable length field, anywhere from 1 to 13 bytes. And that composes what we would refer to as the higher order NSAP octets, which include the system ID and the ENSL. At least 1 byte for the AFI, and the AFI set to 49 plus whatever the area ID is. The system ID itself is what allows us to identify the system within the area. That is a fixed length field, 6 bytes in Cisco iOS, and then the ENSL is an octet that contains the NSAP selector service identifier, 0 for a router, and which would be represented as 00 in the address. And that's pretty much what you're going to see. Remember, we have end systems and we have intermediate systems. End systems would have a different ENSL value than an intermediate system. But because we're talking about routing, we're always dealing with intermediate systems in our particular case. So the total length of the NSAP is anywhere from 8 bytes to 20 bytes total. All right. Cisco routers that route CLNS use the addressing that conforms to the standard. The AFI and the IDIs compose what we call the IDP of the NSAP address, or the initial domain identifier. So the IDP corresponds basically to the major network that the device is a member of. Whenever we talk about IP addressing, we talk about the IP address being broken up into 2 pieces: the network ID and the host ID. So think of the IDP, the initial domain identifier, as that major network. What network do I belong to? Which consists of the AFI and the area ID, essentially, which is the IDI in this particular case. So the AFI byte specifies the format of the address and the overall authority that is assigned to that address. And we already saw some of the values that existed for that. Addresses that we typically would see are going to start with a 49, which are private addresses, again, analogous to the RFC 1918 address space. ISIS routes these addresses, but they should not be advertised to other CLNS networks because they're basically ad hoc, meaning that they're private, right? So other companies might actually use 49 as well. And then, of course, we could have issues with overlapping areas and system IDs and everything else. The IDI identifies the subdomain under the AFI, which in a sense becomes the area ID. All right. The domain specific part, which is really what we refer to as the host portion, so the DSP, the domain specific part, helps with the routing within ISIS. It comprises the what we call the HODSP, the system ID, and the ENSL. The HODSP subdivides the domain into areas, and it's kind of equivalent to like saying the subnet of the network of an IP address. The system ID, as I mentioned previously, identifies, that's the 6-byte component that identifies the individual within that domain, right? The individual OSI device. And the device has an address just like it would in DECnet, but not an IP address in this particular case. And then the ENSL, or the NSAP selector, identifies the process on the device, and that's kind of like a socket in IP, but it's not used in routing decisions. All right, so they have a diagram here that kind of breaks down everything that I just essentially described. The area address is 490001, so the AFI in this particular case is 49. The area ID in this case is 0001. So we can tell because of the AFI and the area ID of 490001 and 490004, 490004, that we would have to have a layer 2 adjacency or an L2 adjacency between those routers because they do sit in different areas. System ID of quad 0, 0 Charlie 11 1111, which is representative of the MAC address of the device in this particular case, and an ENSL of 00. So that's how we essentially identify systems within the domain. All routers within the area have to use the same area address. That area address is going to be used for establishing those L1 adjacencies. Although we could do level 2 routing within the area, typically we will do level 1 routing. And then the system ID identifies that host or that intermediate system inside that area. That obviously will have to be unique for all of the routers within the area. And then the system ID for level 2 routers would have to be unique for the entire domain. Because again, the level 2 adjacencies form a contiguous backbone, which means it extends across the entire autonomous system. Well, we don't really use the term autonomous system in ISIS. We use routing domain, but you get the idea. Okay. The area address identifies the routing area. The system ID identifies the node within the area itself. The first part of that NSAP address is the area address, and that's associated with the ISIS routing process. But unlike OSPF, an ISIS router can actually be a member of only one area because the node goes into the area, not the interface. So all the routers in the same area must have the same area address, which essentially creates that area. All right. The 6-byte NSAP system ID has to be unique within the area. It is, like I said, customary to either use some form of an IP address that's extended with padding zeros or a MAC address from the router because MAC addresses happen to be unique. They happen to be 6 bytes, and that works perfectly for a 6-byte NSAP system ID because they have to be unique and they have to be 6 bytes. The field itself is 6 bytes. That is an OSI directive which Cisco follows. All right. So the last thing we'll talk about in this section here is the ISIS packet header and how that packet header is formed. The first 8 bytes of all ISIS protocol data units are the header fields. We see this in OSPF as well and EIGRP. Every single packet type has a fixed packet header. There's a fixed OSPF packet header. There's a fixed EIGRP packet header. And just like those two protocols, ISIS has a fixed header as well. We don't really call it a packet header because we're not generating packets. We're generating PDUs because it's a layer 2 protocol. And you can see the type length value component that's stored at the end of the PDU is what allows us to carry all that custom information that needs to be exchanged. I don't know that we need to necessarily break down every single field of this header. I will. That's just part of our discussion here. And then we'll wrap up our discussion, and we'll get into ISIS routing logic and operations and some IPv6 stuff as well. So the ISIS PDUs get encapsulated at the data link layer of the OSI model, right? We have 4 general types of PDUs. Just like we have different message types in OSPF, a hello packet, a database descriptor, a link state advertisement, or a link state update, link state acknowledgement, and so on. We have different packet types in the EIGRP, hello, query, update, reply, and acknowledgement. We have different packet types in ISIS as well. We have the IIH, which is basically your hello packet that enables the neighbor detection, neighbor adjacency process to form, 2 types of IIH packets. We have what we call a LAN IIH packet, where we send separate packets for level 1 and level 2 adjacencies. And we have a point-to-point IIH packet, where we send a single packet for level 1, level 2, or level 1 and level 2 adjacencies. Again, not necessarily necessary to know the difference there, but there is a distinction there. Remember, we define 2 different topology types in ISIS, a multi-access, which is our LAN, and point-to-point. So we have basically different types of hellos that are used in those types of environments. We have our LSP PDU. You can think of this as kind of like a link state update in OSPF. So it would be like, how we exchange reachability information. Really kind of the major packet type that we would have in ISIS, being able to exchange routing information using that link state packet PDU. We have a Psnp. Psnp is used to acknowledge and request missing pieces of link state information. So similar to a link state acknowledgement, but not quite the same, because link state acknowledgements don't allow us to request missing information. And then we have a Csnp packet, which is used to describe a list of the link state packets in the link state database of the router. Basically, this is used to tell other routers that the link state packets may be outdated or missing from their database. So when we're exchanging information, OSPF has a similar function. We use sequencing in OSPF, and we use link state age, or LSA age, in OSPF to identify the validity of the link state packets. And if somebody sends me information that is outdated, I have the ability to then inform that individual that their information might be outdated or missing information, and that provides the ability to resynchronize the database and make sure everybody has the latest and greatest information. Very similar to a database descriptor packet in OSPF. All right, so the IAH, that IIS hello, basic ISIS hello, includes whether or not it's a point-to-point link, or whether or not it's a LAN link or multi-access network. The source ID of those hello packets is the system ID of the sending router. The whole time is the time period to wait to hear the hello before declaring the neighbor dead, just like we have in OSPF and EIGRP. The dead interval in the case of ISIS is 3 times the hello interval, but these can be configured values as well. And then the circuit type indicates whether or not this is a level 1 PDU, a level 2 PDU, or a level 1 and level 2 PDU. There's a PDU length field, obviously to describe the length of the data. The local circuit ID on the sending interface. The LAN ID is the system ID of the DIS. That's similar to the concept of a DR BDR, and the pseudo node, or what we call the circuit ID, and the priority field. Just like in OSPF, priority is used for electing the DIS, the DIS, or the DR in OSPF, and the higher the number, the more preferred it is. All right. The source address of our ISIS messages are data link layer addresses. The destination MAC address on our multi-access networks is going to be 0180C2000014 or 0180C2000015. Those are just reserved addresses for that process. All right. So the last thing we're going to talk about in this section is how do we process information? What is the data flow of information, right? We think about this in OSPF and EIGRP, how do we establish an adjacency? How do we exchange information? In OSPF, we talk about the different stages of adjacencies that we go through, the down state, the init state, the xstart, the two-way xstart exchange, loading in full, and so on. And how do we collect the information? Where does that information go? When do we run the algorithm? How do we extract that information, and so on? So the flow of information with ISIS is represented by this diagram here, which is a 4-step process, and then ultimately resulting in what we have in any kind of routing scenario, a routing information base. The routing information base is the link state database and the forwarding database. So the data flow steps are to receive information, update information, make a decision, and forward information. And that's kind of what we're going to break down here, and then we'll wrap up this section. The receive process is the entry point, right? This is obviously by the name, as the name implies, where we receive our information. We can receive routing information. If it's an end system, we might receive user data, error reporting information, and so on. We receive that information, and we report that information to the forwarding process, and then we pass the routing information and control packets like the hellos, the link state packets, etc., to the update process, which is step number 2. The update process generates local link information that gets flooded to our adjacent routers. The update process is what receives and processes and forwards link information, reachability information from my adjacent routers and to other adjacent routers. This is what's going to manage the whole relationship at level 1 and level 2. This is essentially the component that allows us to receive and process and then in turn exchange the link state database information. The decision process is what we would typically identify as now we've collected all of the information. We need to make a decision on how we're going to use that information. So it's basically the algorithm that runs, the shortest path first algorithm. We would decide based on the cost of the links and the metrics, etc., what best paths would exist. We would place ourselves at the center of the tree or at the top of the tree and start to calculate those shortest paths to each of the destinations. So the decision process is basically the algorithm running and saying, hey, I've collected all this information. I now need to decide how I'm going to use that information. And then the forward process, which is the last process, receives that input from the receive process, uses the forwarding database to forward data packets towards their destination. And that is essentially the routing process in a nutshell. All right. So the next thing we're going to talk about is the routing logic in ISIS. The diagram here is the OSI part of the integrated ISIS process. Routing is, of course, routing, right? Being able to identify how to reach destinations. And we've already talked quite a bit about the idea of, what a level 1 system is. And we use the level 1 routes to route within the area, and a level 2 system, we use that to route between areas. We talked about that quite a bit. So, we've already talked about this routing logic concept, basically, and the bottom line is this, right? If I'm a level 1 router, and I'm looking at a destination, and the destination area is not my area, then I'm going to need to send that information over to the next level 1-2 router. It would have to be a level 1-2 router because it still has to be a router within my area, which means it has to be a level 1 router, but it also has to be a level 2 router because we know that the traffic is going to a destination outside of the area. So we use our level 1 database to route by the system ID, which uniquely identifies that destination in the area. For the level 1-2 router, for a destination address. We're going to compare the area ID as well to the area. And if it's equal, we're going to use our level 1 database to route. If it's not equal, then we're going to use our level 2 database to route. Very simple concept. Routing within the area is routing to a collection of system IDs. We have adjacencies for all the routers in the area. We use our Dijkstra's algorithm to figure out what the best path is between the devices, and we route like we normally would based on the cost of links and the cost of paths and so on. We pass the traffic that's destined to travel outside of the area to our closest level 1-2 router. Router between the areas is based on the area address. Level 2 routers in different areas are going to use the area information to exchange area addresses. We're going to use the Ospf algorithm or Dijkstra's algorithm to compute the best path between the areas, and we'll choose that path to route between the areas based on the closest level 1-2 router. All right. We have ESH packets and ISH packets that are used for routers. The end system packets, obviously, we don't really concern ourselves with too much in the context of routing in ISIS, but certainly the ISH packets, the intermediate system packets, are going to be used definitely. So when a host requires needs to do some sort of routing to another host, the packet goes to one of the routers on the network that's directly attached to the same subnet or same broadcast domain as the host. If the destination host is in the same area, the router then searches for the destination system ID and forwards the packet based on least cost routing, based on the overall path cost to the destination. If the destination address is on a host in a different area, the level 1 router is going to send the packet to the nearest L1, L2 router, and we're going to forward that through level 2 routers and continue to reach until we finally reach the area that the destination host is in, and then we can use our level 1-2 router in that area, and then correspondingly or subsequently use the level 1 routers in that area to reach the final destination. All right. All right. Now, this diagram here, we kind of see whenever we talk about OSPF. In fact, it's pretty much the exact same diagram that I use in OSPF to describe the process that a link state routing protocol uses to collect information and process information to make routing decisions, right? We have a link state database. The link state database is essentially a collection of everything that I know, we use our shortest path first algorithm to calculate the shortest path to the destination. Their tree is a little disjointed there, but looks like a bunch of broken branches here. But I'm going to go ahead and place myself at the root of that tree, and then I'm going to start to calculate the shortest path to each destination. And then the best paths are going to end up going into my global routing information base. And that's essentially how the routing process works. All right. So in our case with ISIS, it's really no different. We build our IP forwarding table based on the information that we collect through the link state packets. And the IP information itself is not really part of the calculation of the SPF tree, but we still obviously are trying to route to destinations. When we're running integrated ISIS, the IP information, of course, is included in the link state packets, and IP reachability works pretty much the same way as it would in the case of OSPF. IP information doesn't actually take part in calculating the tree. It's the information about the destinations that we're trying to reach. So the tree itself, we use the traditional CLNS, CLNP information to be able to calculate how to reach destinations. Much like OSPF, where our primary concern is about routing to nodes, not routing to networks. Same thing applies in ISIS. We're trying to define reachability to nodes, not to networks. All right. So this process of collecting this information and processing this information is very similar to what we saw in OSPF. The routes themselves are going to be generated. They're going to be placed in the routing table. And then that's how we identify how we reach destinations. When a route does go into the routing table, they will show up as an L1 or an L2 route, depending on how they were learned through the ISIS process. So when you look at a routing table, you'll have a separate code that will identify reachability for level 1 routes and a different code for reachability for level 2 routes. The separation of the IP reachability from the core ISIS network architecture gives ISIS more stability, more scalability than OSPF. We talked about that briefly before. OSPF sends those link state advertisements for individual subnets, but if one of those subnets fails, we need to flood that information throughout the OSPF domain, and all the routers have to rerun an SPF calculation. In ISIS, the SPF tree is built from the CLNS information, not from the IP information. So if an IP subnet fails in ISIS, the link state packet is flooded just like it is for OSPF, but that failed subnet is a leaf subnet. The loss of the subnet doesn't affect the overall reachability in ISIS because we're not using IP for reachability in ISIS. So think of much like BGP, where network layer reachability information is just data that is transported in the application. The same thing applies here, even though we're operating at layer 2 instead of at layer 7. The CLNS architecture is the underlying architecture that allows the construction of the domain as well as the exchange of the IP reachability information. And yes, we will have to send out, sorry about that, the reachability information, but it doesn't, so we'll have to be able to exchange the updates. Obviously, with the other routers in the topology, you're going to have to be aware of whether or not a destination is going to be available, but it doesn't affect the overall function of the adjacencies, the ability for us to form adjacencies, the ability for us to actually share those link state packets. So the SPF tree is actually unaffected, and the calculation, calculation of that shortest path first tree is not going to be affected as much as it would be in, say, OSPF. So that's a significant difference between ISIS and OSPF. All right. Level 1 routers within the area by default don't carry any information about external routes. These routers are going to use a default route to get out of the area. But in some cases, you may want to leak out routes from an external area into an internal area. And we can also integrate ISIS with other routing protocols like BGP, multi-protocol BGP. We can set up MPLS VPNs and so on. But there is somewhat of a limitation as to how those level 1 routers perform reachability to those external destinations. All routers are going to be defined as a stub. That is the default behavior. So without route leaking, all routers get defined as a stub. There isn't going to be any routing information shared from a level 2 router to a level 1 router. So that's a pretty important concept when you consider that in most ISIS implementations, we're going to have some sort of multi-area design, which means we're going to have those level 2 routers. We basically just simply use the closest level 2 router for destinations that exist outside of the local area, which means that you may end up having suboptimal routing. And by the way, we define the closest level 2 router because our link state database allows us to identify reachability to those level 2 routers, much like in Ospf, where we learn about external destinations from an ABR, and those external destinations can either be represented as type 5 LSAs from an external ASBR or type 3 LSAs for our inter-area routes. We don't use the type 3s and the type 5s to actually route to those destinations. We identify those type 3 and type 5 routes, but we use the type 1 routes to be able to reach the closest ABR. Again, it's kind of the concept of, and I talk about this a lot in my CCIE classes in much more detail, but it's kind of like a concept of routing to a node as opposed to routing to a network. Yes, we know how to get to those networks because they're identified with the type 3 LSAs or the type 5 LSAs, but we make a decision on how to route to those destinations based on the proximity of the ABR that's actually originating that information, because we might actually have multiple ABRs that originate that information. It's kind of the same concept here. We're learning about the external routes from the L2. Well, actually, technically, we're not learning about the routes from the L2 router, but we know that they're external routes because of the area. The destination address that we're trying to route to, the area information doesn't match my local area. So instead of saying, you know what, I need to know specifically how to route to that destination, I'm just going to say, you know what, I'm just going to send the packet to my closest L2 router, right? Because the L2 routers comprise the backbone, which means that L2 routers are going to have complete visibility of all of the routing information for the entire routing domain, as opposed to the level 1 router. So we use that closest level 2 router for destinations outside of the network, but this could result in asymmetric routing, meaning that we're taking one path to reach a destination, we're taking a different path to get back, or we could have just simply suboptimal routing, means we're not using the best optimal path. So ISIS does support a feature called route leaking, where we can take those level 2 routes and we can advertise them into level 1 by a level 1 and level 2 router. Those leaked routes get tagged. They're not going to be re-advertised back into level 2. That's a loop avoidance mechanism, or advertised back to another level 1 and level 2 router. All right. We know what the problem of asymmetric routing causes in a network. If I use a different path, the treatment of the packets might be different, as well as we might have different security functions implemented on the network, which would cause packets potentially to be dropped because we don't have state information for those packet flows, or access control policies might be blocking packets on a certain path, and so on. So with route leaking, we can actually leak that level 2 information into level 1, but this can only be done at the L1, L2 routers. There is an up and down bit in the TLV field, basically a flag that allows us to identify that the route is leaked, so it doesn't get re-injected back into the backbone. All right. For any prefixes that are actually leaked, they have to exist in the routing table as a level 2 route in the first place. We obviously can't originate routes that don't exist in our database. That's just a standard routing 101 concept. Route leaking is defined in RFC 2966. It's called the domain-wide prefix distribution with 2-level ISIS, and it uses a narrow metric type of 128 and 130. We also define route leaking for wide metrics using TLV type 135. All right. Now, as far as actually doing the route leaking, we don't get into the specifics of that, how leaking occurs, but we do obviously talk about the fact that it actually exists. Okay. So as I mentioned before, there is a loop prevention mechanism when we are doing this route leaking. Let's say in this particular topology, we want to make sure that the traffic for the 10.1.1.0 network, which goes from area 3 towards area 5, takes a specific path. All right. So area 5 here and area 3 here. So we want to make sure that we leak the 10.1.1.0 network from the level 2 database in area 5 to the level 3 routers of area 1, because the 10.1.1 destination is, let's see, where it doesn't really show us where that destination is. I guess we kind of have to assume it's in area 3, but, oh no, it's over here, right, area 5, okay. So obviously in area 3, I really wouldn't want these routers going to this L2 router to reach that destination. It's not an optimal path. I want to make sure that we're going to use this path to reach that particular destination. All right. So we would leak out that route from the L1, L2 router in area 5 over to area 3. But we're going to flip that flag to indicate that this is a leaked route. So when that route does finally reach this destination, it's not going to be leaked back out to area 4. All right. So it's just a simple loop prevention mechanism. The specific route for 10.1.1.0 will exist on all the routers for area 3. Keep in mind, guys, that's not how this behavior would normally take place, right? We wouldn't be able to identify the destination prefix specifically. We would just simply know that the destination is not in our area. So, and we make a very simple decision. If the destination is not in our area, we will simply send the packet to the closest L2 router and then let that L2 router make a decision. So without the route leaking, it is possible that we may decide to go this way because that may be the closest L2 router based on the configuration that we might have in our topology. You know, and that would be based on the cost of the links and so on, if that makes sense. All right. So the importance of that up-down bit is a loop prevention mechanism. That if we look at the connection to area 4, because that bit is set, the router is not going to insert that route from the level 1 database into the level 2 database, and the route will not be re-advertised into the backbone. So that will prevent the routing loop. All right. Another concept that we have to be aware of is asymmetric routing. Asymmetric routing is where a packet takes a certain path to reach one destination, and then it takes a different path when it's returning. It is not necessarily detrimental, but it could make troubleshooting an issue. There could be scenarios where if you have additional security policies, like I said, in place, that the routing might not be successful if it's taking a different path. So in this diagram, area 1 contains 2 routers. All right, an L1 router and an L1 and L2 router. One router borders area 2, which was why it is an L2 router, and actually an L1-L2 router, and the other router is in the area, and it's operating as an L1 router only. Area 2 has lots of routers. All right. Some of those routers are operating as L1, and then some of them are operating as level 1-2, obviously for the purposes of communicating to the other areas. There are 3 level 1-2 routers that form the backbone link, that consistent backbone chain across area 2, which is going to in turn link the neighbors in area 1, 3, and 4 together. The middle router of the 3 level 1-2 routers does not link directly to the other areas, but the middle router has to be there to support level 2 routing to make sure that we have a consistent backbone path and that the backbone is contiguous throughout the routing domain. If that middle router fails, then the other level 1 only routers are going to remain level 1 routers, and our backbone will basically be broken. So it's probably not the best design from a redundancy standpoint, but you get the idea. All right. Area 3 contains one router that borders Area 2 and Area 4, but it has no intra-area neighbors. All right. If you look at Area 3, the diagram is kind of cut off there, but it just has a L2 router. All right. The symmetric routing doesn't occur in this particular case because level 2 details are hidden from level 1 routers. The level 1 routers, if you recall, only recognize the level 1 information that they see in their network. They're not going to know any level 2 information. All right. So the level 1 routers are only going to recognize the default route to the nearest level 1-2 router, traffic from router X going over to router Y flows from router X to the closest level 1-2 router, which in that case would be the router just next to it, right? Let me kind of highlight where I'm at here. So we're talking about network X. That's really the only level 1-2 router in area 1. That level 2-1 router then forwards the traffic to the shortest path to the destination through area 2. And then that traffic flows into area 2. It's routed along that shortest path using the intra-area path to router Y. So that's this path that they've documented here. Okay. Router Y routes the return packets to router X via its closest level 1, level 2 router, which would be here. Then, of course, that is then going to send the traffic over that way. It's a really interesting concept. And this is primarily why ISIS uses a standard cost value for all of the links. Because we're using this closest routing concept, the level 1, level 2 closest routing concept. So that means that we have essentially a separate path that's used for routing the packet. Is that necessarily going to be a problem? Not necessarily. It doesn't have to be a problem, but it is certainly something that you have to be aware of when you're dealing with ISIS. Okay. Now, using the same topology, if we were to do symmetric routing by injecting route leaking on the router in area 2 that borders area 1, we can essentially influence that return path for the selection of traffic from router Y to router X. Because in that particular case, we do have knowledge of that destination. We're not just simply routing to the closest level 2 router. We have a specific entry in the link state database for that particular prefix, and we'll use shortest path routing or least cost path routing to reach that destination. You'll notice that some of the links in this topology, most of the links in this topology have a cost of 10. Some of them have a cost of 15. So we're not fixed at that cost of 10 for a particular path. We can certainly use least cost routing in this case. Let's see here. In this particular topology, let's see, 10, 20, 30, 40, 50. So we have an overall path cost of 50 here. Actually, it looks like it might be taking that middle path. I think it's going to be the same cost, but let me go ahead and document it correctly. So 10, 20, 30, 40. So it's a little bit less. All right. Whereas if I were to go this way, 10, 20, 30, 40, same cost, but not symmetric routing. So by leaking the route into the link state database in area 2, we will use the return traffic from Y to X, making that same symmetrical path. And we can influence various aspects of that as well, by choosing that path based on metrics and so on. All right. So the last thing we'll talk about in this section are the different network types. Pretty straightforward. We have 2 different network types, either point-to-point or broadcast. In the broadcast scenario, that's where we would have a Pdus and a pseudo node. I don't know how much detail we're going to get into that, but that's very similar to the DR/BDR process that we have in Ospf. Point-to-point link, directly attached neighbors in a single broadcast domain. All right. All right. So the next thing we'll talk about is basic ISIS operations. One of the things I had mentioned briefly in our previous discussions of ISIS was this idea of what is a Pdus and what is a pseudo node. ISIS is a link state routing protocol, and it requires that all the routers in the same area or the backbone have a synchronized link state database. So when a router floods its link state packet carrying the prefixes, it's important that all the routers receive that information and then they somehow acknowledge that information. This introduces a bit of a problem in a multi-access network like a LAN. And we have a similar concept in an Ospf where we talk about this and the amount of information that has to be processed in a LAN in Ospf. And we have the DR/BDR process to kind of facilitate this. Let's say that we have these 5 routers in our LAN. These routers need to send hello packets to each other when they see the routers, and they will become neighbors, okay? So even though we have the black line represents kind of a logical representation, the red line represents the broadcast domain that we have configured here. All the routers establish a full neighbor adjacency with each other. Unlike Ospf, where the routers only form a full neighbor adjacency with the DR and the BDR. Once the routers are neighbors, they will flood their link state packets to a multicast destination, and all the other routers will receive that link state packet, and they're going to add that information to their database. Let's say, for example, the middle router, the DIS designated router, even though we haven't gone through that process yet, is the one that floods the packets on the LAN. The link state packet from the router might make it to a couple of the routers in the network. But there's really no way for the router, whoever generated that multicast packet, to know. We need to have some sort of acknowledgement so that the router that sends that link state packet knows that that information made it to the other routers in the network. So we could let the other routers send some sort of unicast acknowledgement back to the router, but that's not how ISIS works. And that's what this whole discussion is really all about here. Another issue that also kind of exacerbates this particular problem is that the link state database can actually grow exponentially. If we have 5 routers on the LAN, each router is going to have 4 different adjacencies. There'll be actually multiple neighbor adjacencies to consider in total. So to solve this problem, to solve this acknowledgement problem and to reduce the size of the link state database, we use a special mechanism, and it's called DIS. I call it DIS. Some people call it DIS. Some people call it what it's actually stands for, which is designated IS, or designated intermediate system, like a DR in Ospf. When ISIS routers become neighbors, they also do an additional election on a multi-access network. This does not happen on a point-to-point network, of course, because we can't reduce the number of adjacencies that I can have on a point-to-point network, but they decide who is going to become this designated intermediate system. And it's based on certain criteria. It's based on interface priority. We can kind of see that listed down here. The highest interface priority, the number is 0 to 127. The default value is 64, or the highest SNPA, what we call the subnetwork point of attachment. This can either be based on a LAN, based on the MAC address, in a frame relay network, which is considered a multi-access network. Frame relay can be deployed in a couple of different formats, but one of those is a multi-access format. We'll use the DELC number, the data link connection identifier. If the DELC number is the same, then the system ID becomes essentially the tiebreaker in this particular case. So we can change that priority, but by default on a LAN, the router with the highest MAC address essentially becomes the DIS. And there's only going to be one DIS. There's no concept of a backup router. And the election is preemptive in this case. In OSPF, the election process is not preemptive. In OSPF, once you get elected, you basically maintain that role until you fail and then somebody else takes over. If you do configure a router with a better priority or one that attaches itself to the network and it has a higher MAC address, it's going to become the new DIS router for that particular segment. The DIS is responsible for creating what we call a pseudo node. This is a virtual node created by the DIS, and the pseudo node does two different things. First of all, it creates and updates a pseudo node link state packet that reports links to all of the different neighbors, and it creates a CSNP, what we call a complete sequence numbers protocol. The pseudo node will send this pseudo node link state packet that contains a list of all the neighbors that it is connected to with a metric of 0. That link state packet does get sent to a multicast address so that all ISIS routers actually receive it. This turns that multi-access network into a logical point-to-point topology where the pseudo node kind of sits in the middle. And that's what you're seeing represented by the black lines in this particular diagram. Sorry, I had to take a drink of water there. You talk enough and your mouth just gets dry and you just gotta quench it. This pseudo node design simplifies the link state topology because it reduces the overall number of neighbor adjacencies that you have to consider. All right, the disk to we'll call it R1 on the left, the pseudo node to R1 on the left, the pseudo node to R2 on the left, the pseudo node to R3 on the right, and the pseudo node to R4 on the right. All right. So that's a lot less than the number of adjacencies we would have to have without the pseudo node, where every single router would report 4 different neighbor adjacencies independently. The second task of the pseudo node is to create this CSNP. The CSNP will find a summary of each of the link state packets that was flooded in the area. That's going to contain the link state packet ID, a link state packet sequence number, the link state packet remaining lifetime, and the link state packet checksum. You actually don't find any prefixes inside that CSNP datagram. It's just really a simple overview with the latest link state packets. Why do we need this, right? So let's say that this pseudo node sends out this CSNP packet. So it goes out to all of these destinations. And that contains those 4 elements, right? The remaining lifetime, the checksum, basically everything that's needed to be able to identify the sequence number is pretty important as well. So previously, let's say that the router on the left flooded out, this router on the left had flooded out link state packets. But it didn't know necessarily, using that multicast address, but it didn't know necessarily that anybody else in that network received that information. But it now sees the Csnp from the pseudo node, which includes a summary of the LSP that I just flooded out. So this kind of acts like an acknowledgement. We know that at least the pseudo node has seen this particular link state packet. All right. What happens if the router on the left doesn't see its own LSP in the Csnp? That's going to tell the router on the left that the LAN doesn't know about that LSP that was sent out, and it will flood that LSP again. If one of the routers actually receives the Csnp and sees that one of the LSPs in the Csnp message has a higher sequence number than one of its own databases, then it's going to send out what we call a Psnp, a partial sequence numbers PDU. And that Psnp is a way for us to basically request newer information. Remember we talked about the 4 different kind of basic message types in a previous lesson or a previous part of this lesson? We talked about the different IIH hellos and whatnot, and we talked about the Csnp and the Psnp. This is where this comes into play, right? The Psnp is actually sent out to a multicast address as well. All the routers are going to receive it, but only the DIS will respond to that message. There's no reason to waste network resources getting the other routers to respond when the DIS is really the one that's supposed to be responsible for managing that flow of information anyway. All right. So the Csnps are sent out every 10 seconds. There's going to be plenty of chances for the routers to verify whether or not their latest link state packet information is known on the LAN and whether or not their information is accurate and up to date. All right. All right. So in summary, basically, we have this this broadcast mode of operation, and we talked about the need to kind of have this process built in to reduce the number of adjacencies. That DIS, like I said, is elected. It's going to conduct all the flooding over the network, analogous essentially to the designated router in Ospf. In Dijkstra's algorithm, we actually require a pseudo node, which in this case is represented by the DIS, to build the graph for broadcast media. And we have a similar concept in Ospf with the DR. All right. So the 2 major tasks that are performed by the DIS, as we mentioned, is creating and updating a pseudo node, LSP, and flooding that LSP over the LAN. All right, we talked about the election process and highest priority or the highest SNPA, which is typically going to be a MAC address or a circuit identifier if it's frame relay and so on. Cisco router interfaces have the default level 1 and level 2 priority of 64, like we said before, but it is an adjustable value from 0 to 127, a little bit different than Ospf. In Ospf, it's 0 to 255, and the default value is 1. But in both cases, the highest number wins. The level 1 and level 2 DIS on the LAN could be the same router because, potentially if we leave the default priority, then they're potentially going to, well, they would most likely have the same MAC address. So in that sense, they would basically be the same device. And again, this is a preemptive process, so it's not guaranteed. It's not guaranteed that that you would necessarily stay this DIS role in ISIS. In OSPF, it is non-preemptive. All right. So they do show a table here that kind of talks about what would have to happen if I didn't have this relationship and what would happen if I did have this relationship. This is also a good table to kind of represent how ISIS basically functions over the broadcast network versus a point-to-point network. Obviously, in a broadcast network, we're talking about a single broadcast domain WAN with full mesh, or just a traditional Ethernet network. Point-to-point would be things like PPP, HDLC, or some sort of point-to-point topology in a WAN architecture. All right. The hello timer in the LAN environment is 3.3 seconds for the DIS. Everybody else, it's 10 seconds. And a point-to-point link, it's 10 seconds. The number of adjacencies that I would have to form would be n times n minus 1 divided by 2. That's kind of that exponential factor that describes how many adjacencies I would have to form. We do use a DIS in a multi-access network. We don't use a DIS in a point-to-point network. The link state packets and the hellos are sent as multicast. On a point-to-point link, they're sent as unicast, which would make sense. And we have level 1 and level 2 IIH hellos on multi-access networks, but only point-to-point hellos on a point-to-point network. All right. We already talked about the two-level hierarchy that we have with ISIS, level 1 and level 2. These are completely separate architectures, if you will. We have different link state packets for each of these. We have different link state databases for each of these. The DIS, as we mentioned, sends out that LSP information on behalf of the whole network. It creates and manages that pseudo node representation. And we send out separate level 1 and level 2 LSPs for the pseudo node. The level 1 DIS and the level 2 DIS on the LAN may or may not be the same router as I mentioned before. All right. Now, as far as the hello packets go, those are what we use to establish and maintain our neighbor adjacencies, just like we have hello packets with Ospf and hello packets with the EIGRP. The default hello interval is 10 seconds, but that timer is adjustable. And remember that the dead timer in ISIS is 3 times. And Ospf, it's 4 times. In ISIS, it's 3 times. Okay. All right. Again, these separate level 1 and level 2 hellos are sent out periodically. We use a all destinations multicast address. Now, keep in mind, this is a layer 2 protocol, so we're not using a traditional layer 3 multicast address like 224.0.0.4, 0.0.5 or 6 for Ospf, or 224.0.0.10 for EIGRP, or 224.0.0.9 for RIP. We're using 0180 Charlie 2 000014. That is the all level 1 ISs, and 15 is the all level 2 ISs. We actually have that listed here in the book, so let me go ahead and highlight that. Okay, so 14 is for all level 1 intermediate systems, 15 is for all level 2 intermediate systems, and then we also have some additional multicast addresses at layer 2. 09002 Bravo, that's the multicast destination address for all ISs, and 04 is all N systems. Okay. The default hello timer for the DIS is 3 times faster, 3.3 seconds, 3 times smaller than the interval for the other routers, because the DIS plays such a significant role. It's going to have to communicate information much more quickly. Okay. If a neighbor doesn't send out hellos or doesn't receive hellos within the hold time, 3 times the timer, the default hold timer is 30 seconds, then the neighbor will be deleted and we'll proceed accordingly based on that. All right. Unlike on a LAN where we have separate level 1 and level 2 hellos, on a point-to-point link, we only have one common point-to-point hello format that specifies whether the hello relates to level 1 or level 2 or both. The point-to-point hellos are sent as unicast instead of multicast. Okay? All right. So the next thing we're going to talk about is flooding the LSAs, or the LSPs, I should say. Every intermediate system in the domain has its own link state packets. And again, we create separate link state packets for level 1 and level 2. Those link state packets are identified by the system ID of the router that is originating those link state packets. And a link state packet fragment starts at 0. If we exceed the MTU, they're fragmented into several link state packets, and they're consecutively numbered beyond that. We of course want to try to avoid that fragmentation, but it's not entirely possible based on the fact that we're not sending micro LSAs like we do in Ospf. We're sending much more detailed information. Okay? So in ISIS, this link state packet flooding is a single procedure for both flooding out the original link state packets, for aging the link state packets, for updating them, and so on. So it is more likely that we're going to see large PDUs, and they are going to have to be divided up into smaller pieces. And as I've mentioned several times in ISIS, we maintain a separate level 1 and level 2 database, link state database for these packets. That's also different than Ospf. In Ospf, we maintain a single link state database for all of the different LSA types. We have type 1s, type 2s, type 3s, type 4s, type 5s, type 7s, type 8s, and type 9s, right? Those are the most common LSA types that we'll see in Ospf. And we maintain a single link state database per stack, per v4 and per v6, unless we're running Ospf v3 address family mode, where we maintain one database for v4 and v6. But the idea is that we're containing all of these different LSA types in the same link state database. So when an IS receives a link state packet, it looks at the checksum. It's going to discard any a link state packet that doesn't, the checksum can't be verified. And it's going to flood those with a expired lifetime age. We use LS age in ISIS very similar to how we use LS age in Ospf, although the timers are not quite the same. If a link state packet is valid and newer than what's in the database, we maintain that, we retain that information. We acknowledge it. We give it a lifetime of 1,200 seconds. If you recall, in Ospf, it was 1,800 seconds. And then that age gets decremented every second until it reaches 0. And then that LSP is considered to have expired. But hopefully by that time, we would have already received updated information. And it continues to get basically renewed, I guess, if you will. Once the LSP has expired, it's kept for an extra 60 seconds before it's flooded with an expired link state packet information, indicating to the other devices that this information is no longer valid. We don't need to keep it anymore. Does that make sense? All right. Now, there are two types of SNPs. We talked about the Csnp concept and the Psnp concept. They're used, we use those SNPs differently depending on whether it's a broadcast network or whether it is a multicast network, or point-to-point network, I should say. The Csnps and the Psnps basically have the same format, meaning they carry a summary of the link state packet information. The difference, though, is that the Csnp contains a summary of all of the link state packet information in the link state database, where the Psnp contains only a subset of information. All right? So these SNP packets are used to ensure sequencing and reliability in the topology. The contents we already talked about, basically 4 things in that content. The Psnp is used for acknowledgement of link state packets and to request missing pieces of the link state database. All right. I mentioned actually when we started to talk about the DIS in detail that the Csnp is used periodically by the DIS on the network to make sure that the link state database is accurate and on a point-to-point link when the link comes up. We do send separate Csnps and Psnps for level 1 and level 2 based on those adjacencies. We exchange those Csnps and compare them to our link state database. In a broadcast domain, only the DIS is the one that transmits the Csnps. All the other adjacent neighbors compare that LSP summary that they receive in the Csnp. You know, they're looking for the sequence numbers. They're looking for, you know, the information to make sure that it corresponds to what they expect to see based on their own local link state database to determine whether that link state database is synchronized. In other words, do I have the same database that all the other routers supposedly have in this multi-access network? These Csnps are periodically multicasted out every 10 seconds by the DIS on the LAN. This is going to ensure our link state database accuracy. If there are too many link state packets to include in a single Csnp message, then we send them in groups of messages, right? And that Csnp header actually includes a starting and ending link state packet ID in the range. If they do all fit within one Csnp, we just set that range value to a default value. All right. So in this particular example, router R1 compares this list of the LSPs with its topology table. It realizes that it's missing one LSP. So it says, I have Csnp LSP 76, 77, and 78, but router 1 says, excuse me, the DIS is saying, here is the Csnp information for LSP 76, 77, and 78. And router 1 says, you know what? I missed LSP 77. So the DIS sends out LSP 77, and we acknowledge that we received LSP 77. All right. Remember that message that says I missed LSP 77 is a Psnp message that gets sent to the DIS to request that missing information. And we reissue only that missing information, router 1, that acknowledges that with a Psnp message. Other adjacent ISIS routers use those Psnps also to acknowledge the receipt of the link state packets and to request the transmission of missing or newer link state packets as well. On a point-to-point network, these Csnps are sent only once when the link comes up to synchronize the link state database. Because again, it's point-to-point. So there's really no way to reduce the number of adjacencies that we can have. And we simply have to exchange everything that we have with our neighbor. All right. Now, what are some of the design considerations for ISIS? All right. ISIS does not support NBMA networks. NBMA networks are what we refer to as non-broadcast multi-access. These are networks like frame relay or ATM. We can do what we call pseudo broadcasting in frame relay. So if the frame relay network is deployed as a broadcast network, or if the frame relay network is deployed as a point-to-point model, then we can deploy ISIS over frame relay. But if the frame relay network is operating like a traditional NBMA network, ISIS will not work because we will not be able to support automatic neighbor discovery and the multicasting processes that are required for ISIS to function wouldn't work, because a network that doesn't support broadcasting also wouldn't support multicasting. So special care needs to be taken when we're managing our ISIS topology, especially if we're using a hub and spoke over NBMA or using a full mesh. Some of the design considerations from a hierarchical perspective suggest that a flat ISIS design, where we have all level 1 routers or level 2 routers only, might be better than, say, a hierarchical design. But this all boils down to whether or not you would need to design for scalability. Just like in OSPF, it's the exact same concept. If you don't need to do summarization, if your link state databases are not going to be massive, is there really a need to run multi-area OSPF, right? Would it be potentially just better to simply run a single area OSPF design? So that's a similar concept in OSPF that we talk about often with clients is, why would you, because certainly if you're adding multiple areas, you're increasing the complexity of the overall design of the network, right? So with ISIS, we have the same option. Do I just simply deploy an all L1 network and have a single area? It really boils down to the size requirements of the design. If you're talking about a flat design, you have a single area, 2-level routing is not going to be required. The benefit to that, of course, is that everybody knows about everything. There's full reachability. You don't have to worry about doing things like leaking routes and L1 to L2 route propagation and so on. Also, there's only one link state database, because we would normally have link state databases for L1 and L2, but it doesn't scale nearly as well. All right. So generally, kind of the rule of thumb is let's build for the future, right? Let's build the network with hierarchy in mind. Even if we're not using it today, we might decide to use it in the future. And I think that's why, for the most part, Cisco routers default to L1-2 or L1-L2 because that provides that hierarchy built in. In a hierarchical design, we have multiple areas, of course, positioning the routers, deciding which router is going to be participating in the backbone, whether or not we're going to use any kind of route summarization towards that backbone, whether or not we're going to be using any route leaking to provide optimal routing throughout the topology. All of these have to be considered in the design, which also means that you're also going to have to consider your IP addressing scheme, not only within the area, but globally throughout the entire routing domain. We understand the benefit of summarization. We've already talked about it a couple of different times, right? Summarization reduces the overall size of our link state packets, our link state database. It also hides issues if there's a particular problematic network that continues to go up and down and so on. But it's all kind of the same considerations that we would have in an OSPF design, right? These are the same types of considerations that we have. All right. So it's basically the same types of questions you would ask yourself. So an example that we see here is an NBMA network. How do we work around the issue of forming adjacencies in an NBMA network? As I mentioned before, NBMA stands for non-broadcast multi-access. And non-broadcast means non-multicast. And we know that we already use multicast to be able to establish adjacencies. In this case, the router A interface is defined as a broadcast interface. It's going to send a LAN hello packet. The other routers are configured as point-to-point sub-interfaces. in this example, because this is a point-to-multipoint topology, meaning that all of these routers, by the way, share a common subnet. They're all part of the same broadcast domain. That's why it's called a multi-access network, because they share the same common broadcast domain. But obviously this is going to be an issue because router A is defined as broadcast. It's sending out the LAN hellos. The other routers are sending out the point-to-point hellos. And because of this, adjacencies are not going to form. No routing information is going to be exchanged between those devices. So in a frame relay NBMA network, router A has a multi-point interface. The other ones have point-to-point. The solution would be to simply configure point-to-point sub-interfaces on router A, separate router B, router C, and router D into their own broadcast domains, and just do 3 point-to-point networks. Unfortunately, with ISIS, you can't really trick it. In Ospf, we can change the network types in an NBMA network to kind of trick Ospf into thinking that it's one network or another network, but we can't really do that in ISIS because we really only have 2 network types that we can choose from. We can either choose point-to-point or we can choose LAN. Because of that, we would have to actually change the overall architecture. In a full mesh network, we have some considerations as well. In NBMA networks like an ATM cloud, where all the routers are fully meshed based on virtual circuits, or even a frame relay network where you might have this type of scenario, we need to use the broadcast link type to configure this to work with ISIS. But the problem is in a full mesh ATM cloud, we do not have complete broadcast capabilities. It doesn't act like a traditional multi-point broadcast technology like Ethernet. So if a virtual circuit fails and any-to-any connectivity is lost, we're going to break the flooding model in this particular design. The flooding of routing information is essentially the main concern here. Any change in the network is going to generate a link state packet storm. And with full mesh groups, we can reduce the amount of flooding in the full mesh network by sending link state packets only on selected links. All right, a large non-broadcast multi-access mesh can result in performance issues, scalability issues, excessive flooding in these environments, can be limited by grouping sub-interfaces into what we call mesh groups. And mesh groups are a component of ISIS that allows us to optimize how the flooding takes place over these different connections. Each member of the mesh group doesn't reflood link state packets that are received from other members in the group to the members in the same group because they would have already received that information anyway. But link state packets are received from non-member routers that are flooded to all members of the mesh group and other adjacent non-member routers. So that is a consideration that we would take into account in this type of topology. I mean, the reality is, how much of this are we going to see these days, right? Probably not seeing too much frame relay or ATM out there today. All right. We kind of talked about this concept as well, implementing a flat design versus a hierarchical design. And I think it's relatively easy to understand. Is a single area enough? Do we have a low number of routers? Is there a need for us to run level 1 and level 2? Can I just simply get away with creating just one big backbone? Having level 2 routers everywhere is like analogous to creating just area 0 in OSPF, but you don't even have to do that. You don't actually technically in OSPF or ISIS have to have a backbone if you have a single area. So that area could be a non-area 0 as well. So that would mean in the case of ISIS, deploying a bunch of L1 routers. All right. Now, if I do implement all L2 routers, that will at least provide me the ability to add other areas in the future as needed. Whereas if I run all L1 routers and I want to create a multi-area design or multi-area topology, I'm going to have to convert some of those routers to L2 routers, or at least L1, L2 routers. All right. But again, whether we decide to do a flat design or a hierarchical design really depends on the scale of our implementation, how many routers we have, how many networks we have, all the same considerations that I would have had in OSPF as well. The other option is the hierarchical design. You know, do I create a core? Do I create a non-core area? Very similar to the idea of how do I extend the backbone area in OSPF. You know, if I have a 2-layer model, does the core layer just consist of a couple of routers and then every other router is part of a non-backbone area? Or do I extend area 0 down to those remote locations, etc.? Same concept here. The only difference in ISIS is that we have a virtual backbone that we're creating. There is no physical area 0. So it does make it a little bit easier in this case to kind of segment the network. Our core in this case, which would normally in OSPF be area 0, is actually area 1 in this example. That's because the L2 routers, which go through area 1 and area 2, allow us to create that virtual backbone or that overlay backbone in ISIS. All right. Of course, summarization is a consideration as well. Summarization has the benefit of providing us the ability to ensure that we are reducing the size of our link state database, of the link state packets that we're sharing. And it does directly relate to scalability, right? If I can reduce the size of my link state database, reduce the size of the link state packets, I can reduce the CPU processing and memory usage that's necessary for the domain. But there are some rules, and these are very important concepts that you guys definitely need to understand right here. Internal routes can be summarized from level 1 into level 2. If summarization is used, all level 1 and level 2 routers in the area should be summarizing into the backbone. That's because if we don't do that, you are going to run into a situation where you have some routers advertising a shorter prefix, a summary prefix for destinations, and other routers advertising a longer prefix, the actual networks. And the longer prefix routes are always going to be preferred over the shorter prefix routes. It's longest match routing in the case of routing. So if you don't summarize into from one L1 to L2 router, it's possible that that router would end up being the router that's used to reach those destinations every time, as opposed to the shorter match routes that you would see from a summary. Internal routes cannot be summarized at level 1. That's kind of the same concept in OSPF. We can't summarize unless we're leaving the area. Only an area border router can summarize. Same concept here, basically. We can only summarize into the backbone. External or redistributed routes can be summarized at level 1, but that would be equivalent to like an ASBR summary, even though we don't really call it an ASBR in OSPF. In ISIS, excuse me. All right. We understand what the benefit of route summarization is. We know what the benefit is. It allows us to hide, information, not necessarily hide it, but reduce the number of routes that we have in the link state database. It also allows us to reduce the number of the potential that a topology change could cause routers to have to recalculate their database. All right. In IP, we can only summarize native ISIS routes into level 2 from a level 1 database. It is not possible to summarize internal routes at level 1, but it is possible to summarize external routes at level 1, routes that are being redistributed. Internal routes can be redistributed and summarized from level 1 into level 2. The summarization should be configured on the level 1 and level 2 router that injects the level 1 routes into level 2. If summarization is being used, all level 1 and level 2 routers in the area must be summarizing into the backbone. If I said, and I mentioned this before, one of them is advertising more specific routes, all the traffic from the backbone is going to get sent towards that router because of longest match routing. All right. Internal routes cannot be summarized at level 1 because this is not permitted by the protocol. It is possible to summarize external routes at level 1. All right, so let's take a look at an example. In this example, the core is protected by instabilities in the network because only the aggregate route of all of the distribution and access networks, the 10.1.5.0/24, makes its way to the database of the core. You can see we've got a bunch of /26 prefixes, blocks of 64, and we're summarizing those up to a single prefix. So we would assume that the access layer routers are level 1 and the distribution router is level 2, because that's the only way that this could happen. And that's what we're doing in this case, because we're summarizing from level 1 into level 2. All of the routers in the area should be summarizing. Internal routes, again, cannot be summarized. Summarization on the core to the distribution and access is basically just a default route, because that's the only way that we can get to the rest of those destinations that are off the core there. We can also summarize in other directions, but we always have to follow that rule, L1 to L2. All right? All right. All right, so the last thing we'll talk about in this section is how do we integrate ISIS for IPv6? It's quite simple, actually, because guess what? ISIS is a layer 2 protocol. So it already has the ability natively built in to be able to integrate with IPv6. We support the IPv6 address family configuration. In addition to the OSI and IPv4, there are actually 2 different TLVs that are added. We can see them listed here that are introduced in IPv6. The IPv6 reachability TLV, or hex Echo Charlie, or 236. Echo Charlie happens to convert to 236 decimal. But this reachability TLV describes the network reachability. Meaning what are the prefixes that are available, what are the metrics for those prefixes, and so on. Basically equivalent to an IPv4 internal or external reachability TLV in ISIS for IPv4, type code 128 and 130. Just think of a reachability TLV as basically like routing information. How can I get to this information? And then we have interface address TLVs. These are equivalent to the type 120 or 132 code in IPv4. For our hello PDUs, we have to contain the link local address, especially in IPv6 where the link local address plays such a significant role. For LSPs, we also have to contain the non-link local addresses, which are the global unicast addresses or other addresses that would be assigned to the interface. We also have a new protocol identifier, hex 8 echo or 142. That's the network layer protocol ID. That gets advertised by the IPv6 enabled routers. And the protocol supported TLV, which is type code 129, supports or lists all of the supported network layer protocol IDs, all of the IPv6 enabled routers, advertise a value of 142, and in IPv4 that would be a value of 204. Okay. So the bottom line is we support IPv6. We have some different type codes that we use now to carry information in those TLVs. We have pretty much the same limitations, the same characteristics of ISIS with regard to the different topologies that we support and so on. Whether or not we use a flat design or a hierarchical design, whether or not it's multi-access or point-to-point, same concepts apply. The only difference is we're transporting information slightly differently because it is IPv6, obviously, and not IPv4 in this particular case. There are some restrictions that we need to be aware of as well, especially in a single topology. When you migrate from IPv4 completely to a dual stack environment, there is a discrepancy in the supported protocols that could cause adjacencies to fail. All right, there are consistency checks that the devices run within the hello packets, and if the hello packets don't have the same parameters, the same set of address families configured and so on, then those neighbor relationships will fail. So as an example here, we have a router that's running ISIS for IPv4 and IPv6. It's not going to form an adjacency with a router that's only running ISIS for IPv4 or IPv6 only. Not dual stack, but separately. So we can disable those consistency checks because, technically those are completely different protocol stacks. So we really shouldn't be restricted on allowing those protocol stacks to communicate independently of each other. All right. But in a single topology design, we use the same SPF calculation or SPF process for v4 and v6. It's kind of unsuitable for having a scattered IPv6 support in an IPv4 ISIS network. We can't join, for example, two different IPv6 areas over a v4 only area. The L2 adjacencies won't form. So we're going to end up black holing that traffic into the IPv4 area. Suppressing that adjacency checking on those intra-area links or layer 1 links is done during the transition, I should say, from a single topology to a multi-topology design. So it's supposed to be a stopgap measure. It's not supposed to be a permanent solution, in other words. Okay? In a multi-topology design for ISIS, you can see on the left side there running IPv4 only in area 1. We have an area 1 component that's also running IPv6. On the right side, we have area 4 that's running IPv4, and area 1 and area 2 running IPv6. Area 4 is solely running IPv4. All right. But for IPv6, we don't have the limitations from the design. When we're running both v4 and v6, we run two different SPF instances, which allows the use of different metrics for IPv4 and IPv6. So it's a little bit of an easier migration from a single topology to that multi-topology environment because it's natively supported. All right. All routers in the area or the domain have to use the same type of IPv6 support, whether it's a single topology design or a multi-topology design. If you have a router, for example, that's operating in a multi-topology mode, it's not going to recognize the ability of a single topology mode router to support v6 traffic, which will end up resulting in black holes for our traffic. All right. So that's it, guys. That's it for ISIS. We will wrap up this discussion. And we're going to get into our next section, which is a design case study activity on designing enterprise connectivity. and then we are going to move into our BGP topics. So we'll see you there.